Hello and welcome back to another festive coding session with Mr. Jacob, where we are on the 21st day of December in our Advent of Languages, where we strive to implement the same thing every day in a different language. And what we are going to implement actually is something like an output of this ASCII art Christmas tree in the language of our choice for today, which is ZIG. ZIG is actually a system near programming language, like for example C or Rust or C++ or many others that have been created in over the time. ZIG is actually a quite modern version of that, and I have prepared a certain development environment, kind of, so to speak, here for us. I have created a simple make file here and a Docker file. And the Docker file will simply download a certain ZIG version here that we can actually use, the version 0.13, which is the current one at the time of recording this video, and a little make file, which simply will go ahead and compile our hello.xmas.zig file using this Docker container into an executable that we can then execute. And it will have a target to execute it in this Docker container as well, because I don't want to fight with different image types and system types and stuff like that just for to making this demonstration here easy. So let's just get right ahead and implement some little hello xmas zig before we are going to implement our tree. And in order to do something with this and to output something to stdout, we first of all need access to some way of accessing stdout and writing to it. So we are going ahead and importing the std library of ZIG, which has all of that functionality in conjunction with a lot of other things like memory allocators and different data structures and stuff like that. And this is actually how we do that in ZIG. Then we actually create a public function here, which we call main. And this function will return void. And we will see in a second, maybe this return type isn't the right one, but we will see in a second why and how, and we will actually want to talk about that. And then we can actually use some way to write to stdout. And there are different ways to do that. But first of all, we need to get some sort of reference of stdout. And we can actually get that by accessing stdio, and in this situation get stdout, I think it is. And this would actually give us the file interface or descriptor for that kind of stdout. But what we want is, we want the writer interface. There are no real interfaces in ZIG, but we want actually a struct which has the corresponding methods here, and we get that by calling writer on that. So now that we have that, we can actually do something like stdout, write all, for example, and we can put a string in there like hello xmas, and we can actually end that with a new line here. And we can now save that and hopefully maybe run that, and we will see in a second. It's quickly building the Docker container. It seems I haven't done that. And then it's trying to build it, and then it's telling us that it actually can't do that because the error union is ignored. So let's talk about what an error union is. ZIG actually handles errors much the same way as a lot of different modern programming languages. There are no exceptions or stuff like that. It simply can return something from a function, which might either be a result or it might be an error, or and that's actually done by using error unions in ZIG. And this function here, this stdout write all, could actually fail. You don't know where it tries to write. It simply writes to a writer. So this writer might not be active anymore. It might be closed. The disk might be full, something like that. So it might fail. So we need to indicate that this might actually return an error. And we tell it, if this returns an error, please shortcut this up or cascade this up the calling tree by simply at this moment aborting the execution of this function here and going one level higher up and returning that error there as well. Which means we need to indicate in our return type using this exclamation mark that we might return an error union. So we might return either the value void, so nothing, or an error. and that is actually indicated by this exclamation mark here. You actually, that's a shorthand for having something like std, io, error. I'm not 100% sure about the syntax of this type, but something like we can tell there, okay, we want the union of this type or the type void, the error void. But if you only do an exclamation mark there, it simply infers the error type from the errors that might have been thrown there. The compiler is actually intelligent enough to do that. And using this try as a shorthand syntax of telling it execute this command. If it does not return an error, perfect. And if it returns an error, just bubble this up the execution chain. So let's see what now happens if we execute that. We need to recompile, of course, and it's a hell slow compiling this. Maybe it's part because my screen capturing is running, but as you can see now we have Hello Xmas here. And we now could actually write our Christmas tree functionality out, our rendering Christmas tree. Let me actually get that over here from our README quickly, just as to have some sort of reference there, what we actually want to do here. What I want to do is I want to actually remove those spaces. Yeah, perfect. Okay, so let's quickly comment this one out. I'm not even sure that I actually can comment in Zig like that. Maybe I can't. I don't know. Maybe Zig has another commenting syntax there. Let's just do it like that, just to be sure. Okay, that's our Christmas tree, and we are usually actually printing out those groups here, like this one and this one and this one, to create this nice little zigzag shape. And we could now, of course, write simple functions which will do that by writing out all the different bytes here, which are actually only kind of a stream or a slice of bytes. Strings are only slices of bytes in Zig. And we can actually write them out directly to std out to create our Christmas tree. That would be quite easy and would go very fast, and we would be finished, and it would more or less look like any other language. However, one thing of Zig that is kind of something that is very different to other languages or modern languages is that you are actually really doing manual memory management in Zig these days, and that this memory management is very explicit. And I want to show you this memory management, and this is why we are going to create our whole tree in memory first, which would not be the way to do this if you really would want to implement something like that. It would be kind of inefficient memory-wise and processing-wise. And there are a lot of reasons for it not to do it, but I want to use it to show you how this memory allocation stuff works. So what we are going to do is actually allocating all of the memory for that, implementing this completely or creating this completely in memory, and then writing it out to std out. So first of all, therefore, to have something to get going, I want to kind of refactor this Hello Xmas output into something that actually allocates the space for that and then takes that from a memory location and then writes it out. So what I want to do is something like, I want an fn which kind of does something like maybe, yeah, I don't know. First of all, let's clean up a little, or let's do a little house cleaning there. You will see in a second why we are doing this. Let's call this maybe print tree. And now you will think, wait, he just said he wanted to create it in memory and then print it and not have a separate function for that printing that. That's actually printing it all over again. Yeah, you are right. You will see in a second what I'm doing there. So print tree might actually fail as well. So it will return a void here as well. Okay, so now we have this print tree function, and now we can actually move that there and actually go ahead and call print tree here with groups, which is the amount of groups that we actually want to print here. We have 3 there at the moment, so let's just give it 3 here. Let's call that. Let's put a try at the beginning of that because it might fail. And let's just put that there, and now it will work as it did before. Even though it will not work because we don't use these groups here at the moment, and this will actually create a hard fail in the Zig compiler, because if you don't using a variable, it will simply fail. So we just remove that. Let me write that out just to make sure that we did not do anything wrong there and have actually moved that to another function. Okay, it still works. Nice. So let's go here again into our function now, and let's now see that we do not write out here the bytes, but what we get is we get the std out writer. Okay, that's fine for me. And then we will go ahead and do something like const tree, for example, or let's call that, yeah, we could call that tree or lines. So, and we want something like make tree here, and make tree takes the, and now we can actually now take the groups, takes the groups there as well, and should return us kind of an array of strings which for each line of the tree, and then we can print them out. And that's exactly what we are going here now to do. We are just telling Zig to actually iterate over the lines, and that's how you do that in Zig. You are specifying what you want to iterate over first, and then where it should actually put that. Then we are actually doing something very similar to writing that to std out. However, what we could do here is now we could do write all, or we could use format or whatever. But I think, yeah, why not? Why not use that? And we are simply writing out the line, and then we need to std out write all, or we could just do write, because we now only need to write out one new line character there, 1 byte actually. So now we should actually have printed the lines that we may have gotten from make tree. So let's quickly create an fn make tree here, and it takes the groups, and this one for now will ignore the groups. So let's maybe can't we kind of scroll a little here? Yes, we can. So and we will return here an array, and a slice of slices of U8s, because strings are just arrays of bytes. That's what an array, what a string is, and we want an array, so a slice of those lines, of those strings, so a slice of U8, and it might fail. And how will we actually now return that? The problem here is now that we need to kind of, in this make tree function now, dynamically allocate some memory. And for example, in C, we could now call malloc. We could just call malloc and get some memory. However, that's not the way as it works in Zig, because in Zig, you are using specific allocators for that. The reasoning is that you can then implement different allocation strategies or pass different allocators to different parts of your program with regards to where you have special needs, for example, to optimize certain things. And therefore, we will simply create an allocator here. So we will get an allocator. Let me get one. So the general purpose allocator is usually a good address to start there. So we are getting from std heap, I think there is a general purpose allocator. And we put in an anonymous struct there, or I'm not 100% sure how this is called actually in Zig. It's kind of it creates a type of the specific struct given directly and puts it in there. So we can actually use this as kind of a tuple or a quick key value pair thingy, which is then used there. And then we need to initialize this general purpose allocator. And then in the end, we will actually de-init this thing again, and we will use the defer keyword for that. And the defer keyword is actually a quite nice thing. It will make sure that at the end of this function, everything that has been given to defer at any position in this function is called in the right order. So in the reverse order, actually, that is defined. So it will go up from the bottom to the top and call all of the defer statements. And it doesn't care why or at what position it is called. It might be called due to an error. It might be called to an due to an early return. It might be called to all different kinds of reasons. And that is actually neat, because you can actually put the cleanup code for things you do or things you allocate or something like that directly at the same position as the operation that actually creates this allocation or file handle or whatever you are actually handling there. So that's a really neat thing you can do, and there are other languages out there, of course, that can do that. I think Go, for example, can do that as well. Rust, unfortunately, can't really. However, they are handling it differently in a way that actually works out for them as well by doing it the right style that you would do with C++ kind of as well. So now that we have this general purpose allocator, we of course need to somehow provide it to the functions that actually want to allocate something, because it will only exist in this main function. So what we actually can do is we get actually the allocator out there, because we want kind of the, and again, there are no interfaces in ZIG, but we want kind of the allocator interface. So we want the struct with the corresponding methods there. So we are getting this allocator here, and we are simply now providing it to our print tree. And our print tree now takes an allocator, which is of type std mem, come on, allocator. And as we will need to write this a lot, I don't want to write it out all the time. I'm simply defining above here that allocator is now, I'm sorry, I can't really type today, it seems. Std mem allocator. And I can simply actually assign this type as I could any variable. That is actually a neat thing in ZIG, that it doesn't differentiate between types and variables in most situations. It's a lot more complex than that, but you can actually just do something like that. Okay, so now I have done that. I of course need to pass the allocator theoretically to our make tree as well. However, I don't want to actually take care of freeing every little string that we created there, every little data structure that we created there, for the kind of amount of those make tree of this make tree operation. What I want to do is I want to somehow have some sort of memory space that I can use, that I can easily get chunks out of whenever I need, and I can then do all of this make tree stuff. And at the end of making this tree and having it printed, I want to free everything of all of those memory addresses as well at once. And that's actually where we are using something called an arena allocator. And arena allocators are actually not a specific ZIG thing. It's only that ZIG has an existing implementation of something like that. Arena allocators are actually a way of doing what I just said, of having some sort of memory allocation which works for a whole range of your program. So what you can do there is you are creating a new arena in memory where you allocate a lot of different positions there and get memory blocks out of. You use that, and then and you don't really take care about freeing that again. And at the end of your operation cycle, when you have, for example, closed tasks or something like that, where you can easily do that, at the end of this cycle, you are just throwing away all the memory that might have been allocated. For example, if you are doing something like graphics rendering, you could, for each frame, have an arena. You put all your memory in there that you dynamically need for that frame during that frame creation, and once the frame has been dumped out to your graphics card, you can simply throw away the whole arena and start again. And that's kind of the way how arena allocators work. And if you use them in certain situations, they might even be a lot more performant than usual normal allocation, because you can, for example, optimize allocation by allocating large chunks and then only giving out parts of that to all the different parts of your application that need that memory space there, and deallocating that chunk then in one go again. That can actually make things a lot faster, because you don't have to go to the system kernel every time you need just 2 bytes of memory or something like that. And in our situation here, it makes things a lot easier because we don't need to think about freeing the memory all the time. So what I want now is I want an arena allocator here, which I can actually create by doing something like creating, for example, an ASCII, an arena allocator, an AA. So what we are going to do here is we are simply going to std heap again, and there is an arena allocator already present for us. And we can simply initialize this one by giving it some other allocator that it can actually use to get its initial memory it needs. Yeah. So the arena allocator actually is implemented in an efficient way, which is using linear parts of memory and all that kind of stuff. So it actually goes there and does that. And in the end, I want AA to be deinitialized again. So I do a deferred here. So which means, and that's the reason why I made this print tree function in the first place. Once we are finished with printing out and making and printing out our tree, we will simply throw away this arena allocator and deinitializing it, which will in turn delete the whole arena of memory and therefore free up all the memory that this arena allocator might actually have allocated. So we don't need to take care of that. It will be gone after our print tree operation. Even if we would print millions of trees, it would always free up the memory that it actually used within this creation of the tree. So what I now do is I get the allocator interface again from that allocator. So there it is. And I will simply pass that as an arena to my make tree function here. And now I can actually take that as an arena, which is an allocator as well again. However, I usually tend to name that arena then so that my function that actually takes that knows that it is an arena and that it doesn't need to take care of freeing memory if it's not really that it's not about freeing memory, that it will be somewhere freed in one go at some position, and that someone somewhere or someone else will take care of that. Okay, so now we have our make tree function here, which actually now has an arena allocator. So we can now go ahead and start creating our tree. But what we first need in order to create our tree, because we of course want to now start quickly, and I can guarantee you we are almost there. There isn't. This is now going quite quick after we have all this memory allocation stuff there. What we need here now is we need a way to create actually spaces, because we need those spaces before the slashes and between the slashes and stuff like that. So let's maybe quickly, first of all, create a function which we call repeat, which takes an arena allocator here, which is an allocator, of course, and it takes the number of repetitions that it wants as a usize, and it takes a certain byte as a character that should be repeated. And it will return a slice of U8, so it actually will return a string here, and we can actually then do that. We are doing that, and this might actually fail because it will allocate memory, and this can always fail because we could be out of memory, for example. And now we can actually first of all allocate this byte stream that we need. So come on, we allocate simply, and we need this as a variable. I think no, it will be a const because it will be a pointer. Come on, I can't type today. We are now going to our allocator here and tell it we want to allocate of the type U8, and we want n of those. So we want the space to actually being able to allocate, to store n U8 values. So we are given that memory if it's possible to do that if the memory is not full there. Then we are going to simply, and that's the easiest way to kind of repeat the byte that we have given into the space, we are simply mem setting all of this buffer with our byte C. As we are only setting bytes, should be no problem at all to do that. And then we can actually return that buffer. We know we don't need to take care of it anymore. It has been dynamically allocated, but we know it is in our side of our arena, so it will cleaned up somewhere. So now we have our repeat function here, and now we can actually start making our tree. So what we need for our tree there is first of all our groups. So we need to store the lines that we are now going to create, because they have somehow a dynamic way of growing. We could of course calculate the amount of lines here and pre-allocate that, but I want to show you that you can use those allocators with the std library as well. And that's why we are actually going to create an array list here. So let me do something like let lines, for example, is an array list which actually uses the type of U8. So we want to store U8 slices in this array list, and we want to init that. And now we need to give it an allocator. So the std library types actually are always taking all of those allocators as well if they are doing some sort of dynamic allocation, because this array list, which is something that would be called vector in other languages, for example, is simply a dynamically growing array. So that is actually what we have here, and we should be good citizen here and call a dinit on that, even though we are not actually needing that specifically, because it will clean up the memory and stuff like that of that array list. However, as we are using the arena for that, we will clean that up anyways, but it is not a problem. And at the end of this make tree function, we will even take the thing that we created in this array list and take it out there as a as a slice and take control over that, so it wouldn't even be freed up by this dinit. However, it is still good and best practice to do that. And this is actually where we are going to our return, even though I haven't put anything in that yet. We can actually do that directly by taking the lines, and I think it is to own slice, I think. So this should actually convert this into or take out the data from our lines array list here and give me control of that data. So it essentially should stop the array list from deallocating and freeing that memory once it is deinitialized, and I have now a pointer to that memory and I will take control of it. There is actually not a concept of ownership or something like that as it is within Rust and Zig. However, we are just now having a pointer to this memory area, and now we are the ones that need to take care of freeing it should we no longer need it. As it is in the arena, we don't have that problem, as it will be freed with the arena. So now we can actually quickly do something like we can iterate from 0 to groups here. Come on, 0 to groups. And we want to iterate over this this n here, and for this one we will actually want to go ahead and do something like lines, append slice. So because we are appending multiple entries there, and there is this append slice method for that, and this might fail because it needs to allocate stuff, and then we can simply call make group in here, which we will give the n and the groups, as well as, you have guessed it, the arena, because it will most likely have to allocate something as well. So this call actually will create then the group, which consists of 2 lines, and we will add them there. So let's quickly create this function here, which we call fn make group. And make group actually takes an arena, which is an allocator. It takes the n, which is a use size. I really can't type today. And this is a use size as well. And what will it return? It will return a slice of a U8. So it will return a list of strings, kind of, you could say. So now, how do we actually do that? First of all, we need some spacing. We need the spacing for each of those groups. So we need the spacing outside of this tree, and we need the spacing inside of this tree for this specific group. So let's quickly create that. We have outside, and we have our repeat function created, which actually, by the way, could fail. So we need to have a try here, and we need, of course, to make this return an error union because it could fail. So what we actually want to repeat, and we give it the arena to allocate a proper memory for that, we want to actually repeat on the outside groups minus n times the byte, which actually is this character, this space character. So now we have that. And we want inside as well, which is try, repeat, arena, and this is actually n times 2, the space here. Now we have that, and now we need to create the string with the spaces, the slash, the spaces again, and the backslash. And we can actually use an std library function for that again, which is actually std format, I think, and I think it is something like alloc print. There is a format as well which could be used to actually print directly to std out. We didn't do that before, but this one actually uses the given allocator to allocate a memory and return you the string. So we should actually call that here line 1 or something like that. 1, not 2. And we want to alloc print something, and now we give it a format string here, and we want a space and a string there, then we want a slash, and then we want another string there, and then we want a backslash there. And yeah, we could use specific formatting syntax here to, for example, pad the string with spaces as well, and we could have kind of not needed to implement the repeat function there and stuff like that. However, I thought it might be a good idea to do that just to show you how it works. So, and formatting, using the formatting capabilities we have done a lot of times before in other of those videos. So what we now provide here is again such an anonymous struct, which actually takes then the 2 arguments that we want to put in there, so the outside and the inside. And then we should actually be ready. And this can, of course, fail because it is allocating memory as well, so it could fail. So now we have our line 1, and now we need line 2. So what we actually do here is we simply copy that. We then remove those variable thingies here, because now we want to kind of reuse that, because var means it's mutable, where const, and we can make this line const, where const means it's immutable. So this will be line 2. And now we are putting a new string here into that, which is 1 shorter, because we are going 1 further to the left. And here we will make the inside as big as the next group. That is actually what's creating the zigzag shape. And then we are kind of allocating and printing exactly the same formatting string here. And usually you would now need to take care of freeing the memory that we actually allocated above here, because now we are simply allocating new memory but not freeing the old one. But this is where the arena comes in again. So as we are doing it in an arena, we have those memory allocated somewhere, and we don't really care about it, and it will be deallocated and freed once the whole arena is freed, after our tree has been printed. Which is no problem here, because it's only a couple of bytes there. So now that we have done that, we are actually using our arena again, because now we need to allocate somewhere memory space to actually have pointers, to have a list of 2 pointers to those byte slices, because we are going to actually return that. So what we are going to do here is we are return try arena dupe, and that's actually the quickest way to return this kind of dynamic list of the 2 lines that we want to create there. So we are returning a duplication of the reference of this struct that we are creating here now, from line 1 to line 2. So essentially this is creating a duplication of the pointers list that is pointing to line 1 and line 2. So it's not duplicating line 1 and line 2. It's just kind of returning the correct memory address, which is now allocated within the arena, to this array, which has references to those lines that we have kind of allocated here before. So now we should actually have everything ready to make our groups, and therefore we should actually be able to print out the first part of our tree here. If I did this right and there is no error. So there is an error in line 2. Come on, all void 60. Okay, yeah, that's, I guess I see the problem there. Line 16. Actually, the d init here is returning a value, and we actually did not handle that. So I'm not just now ignoring it with setting it to underscore, because Zig actually has a compile error for variables that we don't use. And finally, we have printed out our first part of the Christmas tree. And now let's quickly finish this up, because this video is already much too long. So I guess once we have the groups, we need this divider line below our tree there. We can actually simply create that and append that, creating our repeat function here. So let's put a try in before that and a try before that, because both of that things might fail. And we give this repeat thing our arena, and we tell it that we want groups times 2 plus 2 repetitions of the minus sign there. And this should actually do our lines there. And let's compile that. And in the meantime, while this is compiling, let's create our try, lines, append, slice, and we want actually something like try, make, trunk, and we give it groups, and of course we give it the arena again as well because it might be needed there. And now we need to implement that, of course. So let's implement make trunk, and it takes an arena allocator, and it takes the groups, which is a usize here, and it returns a slice of lines there, and actually it may fail. That's why we do that. So let's go ahead and quickly get some spacing here, which is the outside spacing again. So we are using repeat here again that we wrote before. It takes the arena, it takes the number of groups because that's essentially how many spaces we need there, and we want space there. And now we can actually create our line here using std format alloc print again, and we are giving it arena again, and now we are giving it the formatting string for our trunk signs with the spacing before that, and then we actually want just the outside there inside our string. Okay, let's go get that, and this might actually fail, and this might actually fail as well. And now we can return simply an arena, and we can dupe the, and we need to try that, of course, as well. And we can elements of U8 slice, and we are doing the same as we did before. We are simply putting those lines there, and now you can see that those are really references because I'm simply creating a list of references where we reference the same line 2 times, and this should work out in the end as well. And now we have our divider line, and if I now compile this again and run it, we should actually have our trunk there as well. And no, of course we do not, because I have kind of fucked up a return type again, didn't I? Yeah. Okay, so let's quickly remove that there. Let's go back in here and compile it and create our tree, and hopefully we now have a tree. Come on, Zik, give us a tree, Yes, we have a Christmas tree. And maybe now let's make this a little bit bigger here, something like, I don't know, 7, for example. And let's do this one more time. And yeah, and there we have it. There we have, hopefully in a second, a Christmas tree, a big Christmas tree done in Zig. And yeah, we did this with dynamic memory allocation. And let me point out again that you would normally never do this program like this. You would print it out simply to std out because it would be more efficient, more memory efficient, it would be a lot faster. It would be less error prone. It would be less code. It would simply be better, and you would not do it like that. However, I think this maybe showed you, or hopefully showed you, how this memory allocation thingies in Zig work, and how you can actually do that. And yeah, if you had fun and enjoyed this video, maybe take a look at Zig if you want to. Just download it and browse around in it and maybe play with it. And I hope you had fun joining me today, taking a very little and fast look at how Zig works, how it looks, and what it does in terms of memory allocation. And you will join me in the next 2 sessions until we have, in the third one then on the 24th, our big finale, which I've already planned out, and I think that will be a little bit special again. And I hope you will join me on the next sessions. And if you haven't seen the ones before that, just quickly check out my channel. Please give the video a like if you liked it, and maybe check out the other videos there. And yeah, have fun joining me in all of those coding sessions. I hope to see you in the next one. Bye!